All right, welcome to the deep dive. Today, we're going to be taking a look at quantum logic.
Oh, quantum logic.
Yeah, and like, how quantum mechanics kind of throws a wrench into our classical way of thinking about logic.
Yeah. It's really fascinating how these two things interact because the success of quantum mechanics really challenges a lot of assumptions that we've had in classical physics.
Exactly, yeah. And one of the biggest ones is like logic itself. Yeah.
Yeah, it's amazing how it impacts our ideas about logic.
Yeah, so to get started today, we've got some excerpts from the Stanford Encyclopedia of Philosophy's entry on quantum logic and probability theory.
Ah, yes, that's a great source for understanding this.
Yeah, so we're going to be diving into that, and I think it'll be a really mind-bending journey. So buckle up, folks.
Yeah, get ready for a wild ride.
Okay, so before we get too far into the weeds here,
Mm-hmm.
can you just give us like the super simplified version of how quantum mechanics views the world? Explain it to me like I'm a philosopher who maybe hasn't cracked open a physics textbook in a while.
Okay, so in classical physics, right, everything's about certainty. You've got a ball, you know its position, you know its speed, and you can predict where it will be.
Right, nice and neat.
Exactly, yeah.
Okay.
But quantum mechanics introduces this inherent uncertainty. So instead of saying the ball will be at point X at time Y, we say there's a certain probability of finding the ball at point X at time Y.
Okay, so it's a shift from like definite properties to
Yeah.
probabilities.
Exactly.
Like I don't know, it's like the difference between like knowing the exact temperature for tomorrow versus getting a weather forecast that says like 30% chance of rain.
Yeah, that's a perfect analogy, and this move to probabilities really has huge philosophical implications. It suggests that the universe might be fundamentally indeterministic at its core.
Right, yeah. And it makes you wonder like what it even means to know something, if everything's just like a probability.
Yeah, exactly. It really challenges our classical notions of knowledge.
Totally. So, where does John von Neumann fit into all of this? I know he was a big player in the development of quantum mechanics.
Yeah, von Neumann was a brilliant mathematician, and he saw that these probabilities in quantum mechanics, they weren't just, random numbers. They actually had a deep connection to these mathematical objects called projection operators.
Okay, projection operators.
Yeah, projection operators, and these guys operate in this space known as Hilbert space.
Okay, Hilbert space. That sounds a little intimidating. Is that where the math starts to get really hairy?
Yeah. Well, you can think of Hilbert space as kind of an expanded canvas, right? So in classical physics, we might describe a particle's position with a point on a line. But in Hilbert space, we can describe not just position, but a whole range of properties, even ones that, seem contradictory from a classical point of view.
Right. So it's like we're going from a flat two-dimensional image to like a three-dimensional, holographic projection.
Exactly, yeah.
And each point in that Hilbert space is capturing like a much richer picture of the particle state.
Exactly.
And these projection operators you mentioned, they help us navigate this space, right?
Exactly. They tell us the probability of finding the particle in a specific state when we make a measurement.
Right. So it's like they're projecting that full quantum state onto a particular outcome we're interested in.
Exactly. Yeah.
Okay, cool. So we've got our heads around probabilities. We've got these projection operators hanging out in Hilbert space. But how do we get from there to quantum logic? It seems like we're jumping from like math to philosophy.
Yeah, and that's where things get really interesting. These projection operators, they don't just describe probabilities, they actually form their own kind of logical structure.
Okay.
It's called quantum logic, and it doesn't quite follow the same rules as the classical logic that we're used to.
Wait, so different rules of logic.
Yeah.
You're telling me that like the way we reason, the fundamental principles of like truth and falsehood could be different in the quantum world.
Yeah, it's a radical idea, but that's exactly what quantum logic suggests.
Wow.
And one of the most striking differences is the breakdown of the distributive law, which is a cornerstone of classical logic.
Okay, back up for a second. For those of us who aren't logic whizzes, remind us like what the distributive law is all about.
Sure. So the distributive law basically says that the way you group things in a logical statement doesn't change the truth of the statement. So, for example, I like apples and I like bananas, or I like oranges.
Okay.
That's the same as I like apples and I like bananas, or I like apples and I like oranges.
All right, yeah.
It's like the order of operations in math, you get the same answer whether you add the numbers inside the parentheses first or you multiply them out.
Right, yeah, it all works out.
Yeah, exactly. But in quantum logic, this basic rule doesn't always hold.
Okay, it doesn't hold. Why not?
Yeah, so and the reason has to do with the way we measure properties in the quantum world.
Okay.
So take for example a particle's position and momentum. So in quantum mechanics, the more precisely we measure a particle's position, the less we can know about its momentum and vice versa.
Right, that's Heisenberg's uncertainty principle.
Exactly. Yeah.
So if I try to like pin down the particle's location, its momentum becomes like fuzzy, and if I
Yeah.
try to like nail down its momentum, then its position gets all uncertain. Okay, I got it. But how does that break the distributive law?
Right. So imagine statement A is the particle's position is within this range. And statement B is the particle's momentum is within this range.
Okay.
So in classical logic, A and B or not B, that's always equivalent to A and B or A and not B. But in quantum logic, because of this this inherent uncertainty, the way we group those statements can actually change the outcome.
Wait, be or not be, that should always be true, right? Either the momentum is in that range or it isn't.
Right. And in classical logic, yes.
So how can that change depending on how we group it with the position statement?
Well, that's the strange thing about quantum logic, right? Because we can't simultaneously measure position and momentum with perfect accuracy. So those statements about position and momentum become intertwined in a way that violates that distributive law. It's as if the logic itself is sensitive to the limitations imposed by quantum mechanics.
Okay, my mind is officially bent. So we're saying that like this fundamental principle of logic, something that seems like completely self-evident in our everyday world, just goes out the window in the quantum world. That's a pretty radical departure.
It is, and it has profound implications for our understanding of the nature of properties, truth, and even reality itself.
Oh man, all right. Well, that's a good cliffhanger. We've got probabilities, we've got projection operators, and now this mind-blowing breakdown of the distributive law. I'm definitely ready to dive deeper into this quantum logic rabbit hole.
Yeah, me too.
All right, so stay tuned.
Yeah. And welcome back to the deep dive. We're continuing our exploration of quantum logic.
Yeah, it's like we're venturing deeper and deeper into this this strange and wonderful quantum realm.
Exactly, where the familiar rules of classical logic start to break down.
Right. Yeah, we've already seen how quantum mechanics replaces those nice, neat certainties with probabilities and introduces us to these mysterious projection operators that kind of act like guides in this vast Hilbert space.
Yeah, and last time we left off with this really mind-bending realization that one of the cornerstones of classical logic, the distributive law, just doesn't hold up in the quantum world.
Yeah, it's like the logic itself is adapting to this inherent uncertainty of quantum mechanics.
Yeah.
But where do we go from here? I mean, does this mean we have to completely abandon like our classical way of thinking?
Well, that's the million-dollar question, isn't it? Some physicists and philosophers have tried to reconcile quantum logic with classical logic to find a way to make them play nicely together.
Okay.
And one approach is to try and embed quantum logic within a classical framework.
Embed, is that like trying to fit a square peg in a round hole?
It's a good analogy. Imagine you're trying to represent a three-dimensional object on a two-dimensional surface.
Okay.
Right? You can capture some of the features, but you inevitably lose some information in the process.
Right.
And embedding quantum logic into a classical framework is kind of like that.
So we're basically trying to like project the strangeness of quantum logic onto the more familiar terrain of classical logic.
Yeah.
But you're saying that something always gets lost in translation.
Exactly. So, for example, think about a quantum system with a limited number of states, right?
Sure.
In classical logic, every subset of those states corresponds to a property. But in quantum logic, only certain subsets, those described by those projection operators we talked about,
Right.
those are considered properties.
So it's like we're trying to squeeze a more nuanced, multifaceted quantum world into the simpler black and white categories of classical logic.
Precisely, yeah. And sometimes you can pull it off by expanding the classical state space, making it bigger to accommodate those quantum properties.
Right, so we're kind of stretching the boundaries of classical logic to try to make room for the quantum weirdness.
Yeah.
But you said there were caveats. Like, when does this embedding strategy fail?
Well, the problem is that quantum logic has these inherent non-classical features, right?
Right.
Like the breakdown of the distributive law. That can't be fully captured by any classical embedding. It's like, trying to flatten a crumpled piece of paper. You can smooth out some of the wrinkles, but you can never completely erase the creases.
Okay, so those quantum quirks always find a way to poke through, no matter how hard we try to force them into a classical mold.
Yeah.
Are there any other ways to try to bridge this gap between quantum and classical logic?
Well, another approach involves introducing what are called contextual hidden variables.
Okay.
It's a mouthful, but the idea is that you can recreate those statistical predictions of quantum mechanics
Right.
if you allow for hidden variables that depend on the context of the
Yeah.
measurement.
Contextual hidden variables. Break that down for me. That sounds even more complex than the embedding idea.
Okay, so imagine you're measuring a particle, right?
Yeah.
And you have two different ways to measure it, A and B. So in quantum mechanics, the outcome of measurement A could depend on whether or not you've already measured B, and vice versa.
So the act of measuring one property can influence the outcome of measuring another property. That sounds a bit like those observer effects we hear about in quantum
Yeah.
mechanics.
It is, and a contextual hidden variable theory would say that there's a hidden variable that determines the outcome of each measurement.
Okay.
But here's the value of that hidden variable changes depending on which measurement you're making.
Okay, so it's like saying the particle has like a secret set of instructions, but those instructions change depending on which question we're asking.
That's a great way to put it. It's a clever way to try and sneak those hidden variables back into the picture, even after Gleason's theorem seemed to rule them out.
Right, right.
But this solution comes with a price.
I have a feeling this price is going to be pretty steep. What's the downside of bringing back those hidden variables?
The price we pay is non-locality.
Okay.
So a contextual hidden variable theory has to allow for the possibility that measurements on one part of a system can instantly affect measurements on another part, no matter how far apart they are.
Whoa, faster than light influences. That's even weirder than the breakdown of the distributive law.
It is.
Didn't Einstein famously reject the idea of spooky action at a distance?
He did, and this
Yeah.
this inherent non-locality is one of the main reasons why many physicists and philosophers are skeptical of contextual hidden variable theories.
Yeah, it does seem to clash with our intuitive sense of cause and effect.
Yeah.
If something happening over here can instantly influence something happening over there, even if those two places are, light years
Yeah.
apart,
Yeah.
then our whole understanding of how the universe works just seems to break down.
Exactly. It challenges our very notion of causality and locality, fundamental principles that we rely on to understand the world around us.
Right, yeah. So we can try to force quantum logic to fit into a classical framework,
Yeah.
but we end up with either an incomplete picture or these mind-boggling non-local effects.
Right.
It seems like quantum logic is truly a beast of its own,
It is, and one of the most intriguing and perplexing aspects of quantum logic emerges when we start talking about composite systems, where multiple quantum systems are combined.
Okay.
And this is where things get really, really interesting.
Composite systems. So, like, instead of looking at one isolated particle, we're looking at a whole bunch of them interacting with each other.
Precisely, yeah. And what we find is that combining quantum systems leads to behaviors and logical structures that defy our classical intuitions. In fact, there's a famous example called the Foulis-Randall example that illustrates this point beautifully.
Okay, the Foulis-Randall example. I'm all ears. What makes this example so special?
So picture a simple quantum system, right? Say a particle that can be in one of three states.
Okay.
We can describe this system using a test space, which is basically a collection of of possible measurements you can perform.
Right.
And in the Foulis-Randall example, they use a test space with 5 different measurements, each with 3 possible outcomes.
Okay, 5 measurements, 3 outcomes. That doesn't sound too outlandish. What's the catch?
Well, the catch is that when you combine 2 of these simple systems together, the resulting system is no longer orthocoherent.
Orthocoherent. That word rings a bell, but I need a refresher. What does that mean again?
Orthocoherence, it's a fancy word,
Mm.
but it captures a pretty intuitive idea. It basically says that if you can measure a bunch of properties in pairs, you should be able to measure them all together as well. It's about consistency.
Yeah.
So if you can test each piece of information separately, you should be able to test them all at once.
So it's like saying that if I can check if a cat is alive or dead, and whether it's black or white separately, I should be able to check both of those things simultaneously.
Exactly. But you're saying this breaks down in the Foulis-Randall example.
Okay.
Exactly. When you combine 2 of these Foulis-Randall systems, you can create a set of propositions that can be measured pairwise. But when you try to measure them all together, it's like the logic itself crumbles. The system is no longer orthocoherent.
Wait. So just the act of combining these systems leads to this logical inconsistency. It's like 1 + 1 suddenly equals 3.
That's the surprising thing about quantum logic, right?
Yeah.
It challenges our assumptions about how systems should behave when they're combined. It's as if the whole is greater than the sum of its parts in a very strange and counterintuitive way.
Yeah, this is blowing my mind. It's like the logic itself gets entangled, just like those particles we hear so much about in quantum mechanics.
That's a great analogy. And there's another result, Artz's theorem,
Okay.
which adds another layer of intrigue to this whole business of composite systems.
That's his theory. Okay, meet with it. What does this theorem tell us about composite systems and their quirky logic?
So Artz showed that if you start with two quantum systems that satisfy the conditions of Pyron's theorem, which if you recall tries to bridge the gap between quantum logic and Hilbert space.
Right. Right.
Then when you combine them, the resulting system can only satisfy those conditions if at least one of the original systems was classical.
Hold on. Let me get this straight. We start with two perfectly good quantum systems that fit nicely into this quantum logic framework. We combine them, and suddenly the combined system can only keep working within that framework if one of the original systems was actually classical all along.
Mm.
That's like mixing 2 primary colors and ending up with a shade of gray.
Yeah, it's counterintuitive to say the least.
Yeah.
But that's the beauty of quantum mechanics, right? It keeps throwing curveballs our way, challenging our deeply ingrained assumptions about how the world works.
Yeah, this is incredible.
Yeah.
It seems like the simple act of combining quantum systems unleashes a whole new level of strangeness.
Yeah.
It's like the quantum world has its own set of rules for togetherness, and those rules are radically different from what we're used to in the classical world.
Yeah, and that quantum togetherness is what we'll be exploring in the final part of our deep dive.
Oh man, I can't wait.
Stay tuned.
And welcome back to the deep dive. We've been on this incredible journey through quantum logic.
Yeah, it's been quite a wild ride.
It has. It's like we've been spelunking through the caverns of quantum logic, and it's really challenged a lot of our assumptions.
Absolutely.
Yeah. So far we've seen how quantum mechanics replaces certainties with probabilities, how it introduces these mysterious projection operators.
Right.
And even how it challenges like the very bedrock principles of classical logic.
Yeah, like the distributive law going out the window.
Yeah, exactly. And last time we were left kind of teetering on the edge of this quantum togetherness cliffhanger.
Yeah.
The idea that combining quantum systems leads to even more bizarre and counterintuitive logical behavior.
It really does. And this is where things get really interesting, where quantum logic starts to shed light on some of the biggest unsolved mysteries in quantum mechanics.
Okay, I'm on the edge of my seat. What mysteries are we talking about here?
Well, one of the biggest head scratchers in quantum mechanics is the measurement problem.
Right, right.
A system can be in a superposition of states. Think Schrodinger's cat being both alive and dead simultaneously.
Right.
But when we make a measurement, we always get a definite outcome.
Yeah, the cat's either alive or dead.
Exactly, yeah. It's not both.
Not both.
Yeah. So how does that happen? Where does that superposition go?
Right. Yeah, it's like the act of measurement forces the quantum world to make a choice.
Yeah.
It collapses those multiple possibilities into a single reality.
Exactly.
But how does that work?
That's the million-dollar question. And this is where our exploration of composite systems and quantum logic offers some potential answers.
Okay.
One idea is that the measurement process itself is a kind of interaction between the system being measured and the measuring device, which is of course another quantum system.
Right, right.
So the measuring device isn't just a passive observer; it's an active participant in this quantum dance.
Right. Yeah, yeah. It's getting in on the action.
Exactly. And when these two quantum systems interact, their combined logic might behave in a way that forces a resolution of that superposition.
Okay, so I think I'm starting to see where you're going with this. Are you suggesting that the collapse of the superposition happens because of the way the system and the measuring device become entangled?
Yeah.
Like their combined logic just says no more superpositions allowed.
Yeah, that's one way to think about it. It's as if the logic of entanglement, the rules governing how these systems are connected,
Right.
drive that transition from a fuzzy, indefinite superposition to a sharp, definite outcome.
So the measurement problem isn't just about like finding a better way to describe what's happening. It's about understanding how the logic of entanglement shapes the very fabric of reality.
Precisely.
That's pretty mind-blowing. That's
Yeah.
the measurement problem is like inextricably linked to this deeper mystery of how quantum systems come together and relate to each other.
It is, yeah, and it brings us to another major puzzle in quantum mechanics.
Okay.
Entanglement itself.
Right, yeah.
What is the nature of this spooky action at a distance
Right.
that Einstein found so unsettling?
Right, yeah. How can two particles be linked in such a way that they seem to influence each other instantaneously even when they're, light years apart? It defies our classical intuitions about space and time.
It really does, and that's where quantum logic can help us move beyond just saying entanglement is weird.
Right.
It provides a framework for describing those correlations between entangled particles in a precise and rigorous way.
So instead of just like throwing our hands up in the air and saying it's spooky action at a distance, we can actually use quantum logic to articulate the specific ways in which those entangled particles are connected.
Exactly. Quantum logic allows us to formulate statements like, if the spin of particle A is up, then the spin of particle B must be down, even when those particles are separated by, vast distances.
Wow, that's amazing. It's like quantum logic is giving us a language to express the subtle and profound connections that exist in the quantum world.
It is, and it's not just about describing those connections. It's also about understanding the implications of those connections.
Okay.
So quantum logic can help us explore how the entanglement of systems affects their combined logic, how it influences the emergence of new properties, and how it might even play a role in the very structure of space-time.
So we're not just using quantum logic to describe what we see. We're using it to probe the deeper mysteries of the quantum realm.
Absolutely, yeah.
Mysteries of measurement, entanglement, and perhaps even like the nature of reality itself.
Yeah, it's a journey of exploration, of pushing the boundaries of our understanding.
Yeah.
And as we delve deeper into quantum logic, we might find that we're not just revising our understanding of the universe.
Yeah.
We're also revising our understanding of ourselves.
Yeah, that's both exhilarating and daunting at the same time.
It is.
But that's what makes these deep dives so rewarding. We get to grapple with these really profound questions, expand our minds, and catch a glimpse of the universe's hidden secrets. Well, on that note, it's time for us to surface from this deep dive into quantum logic.
Yeah.
To our listeners, we hope you've enjoyed this journey into the quantum realm.
I hope you've had fun.
Yeah, and we've seen how quantum mechanics really challenges our assumptions about logic, about reality, and about the nature of knowledge itself.
Yeah, and as you continue to explore these ideas, remember that the quantum world is full of mystery and wonder.
Yeah.
It invites us to question, to explore, and to embrace the strangeness that lies at the heart of reality.
So keep those thinking caps on, stay curious, and until next time, happy diving.
Yeah, happy diving.